Start now.
Yeah, I can start.
So, yes. So, hello, everybody. Welcome to the European Non-Associative Algebra seminar. The speaker of today is Justin McInroy from the University of Chester. He will speak on the classification of quotients of the Highwater algebra. Yes.
Tu as entendu cette interférence?
Oui, oui, oui.
Ah, intéressant.
Okay, thank you very much for inviting me to speak here. So this is joint work with Clara Franchi and Mario Mainardis, who I think I saw on this call as well. I'm going to talk you through the classification of quotients of the Highwater algebra. So this is to do with axial algebras, so I will give a sort of brief bit of motivation for them. I will give you some definitions and things. I think Clara spoke last week, so she will have introduced you to a number of the concepts there already, but I'll go over some of these. And then I will get to sort of why we want to do this. And then the last bit of the talk will be actually what the classification says. Okay. So axial algebras are a relatively new class of non-associative algebra, and they have this strong natural link to groups. So I'll say a bit more about that in a minute. But in terms of examples, so the Griess algebra is an example. So this is perhaps one of the main motivating examples. So the Griess algebra has the property that the monster simple sporadic group is its automorphism group. Axial algebras also axiomatize various properties found in vertex operator algebras. So for example, the moonshine VOA. Most Jordan algebras are examples. In a sense, I can make precise in just a minute. But recently, examples have been found elsewhere too. So for instance, Hessian algebras in the theory of nonlinear PDEs. And also axial type behavior has been speculated in various other areas, such as algebras of vector flows on manifolds. Okay, so often non-associative algebras are defined by some kind of identity or identities that elements in the algebra must satisfy. However, axial algebras are not defined in this way. So they're defined in quite a different way. So I want to give you sort of a high-level view of how axial algebras are defined, and then I will drill down a bit and tell you what some of the words mean. So from a high level, an axial algebra, or maybe an F axial algebra, is a commutative non-associative algebra which is generated by a set of F axes. So it's just an algebra which is generated by a set of special elements. What is this F? Well, F is a fusion law, and its role essentially gives us partial control over the multiplication in the algebra. And I'll make that precise in just a minute. But the key property that axial algebras have is that for every axis, we can associate an automorphism of the algebra, and we call this a Miyamoto involution. And if we can collect together, or if we do collect together all of these Miyamoto involutions, these are going to generate a group, a subgroup of the automorphism group, and we call this subgroup the Miyamoto group. So this, if you like, is a naturally associated subgroup of automorphisms connected to these axes which generate the whole algebra. So it's in this way that there's this naturally associated group to the algebra. Okay, so let's drill down and say what actually some of these words mean. So an axial algebra is just an algebra, a non-associative algebra, which is generated by a set of axes. So I should tell you what an axis is, and maybe I should also tell you what a fusion law is. So a fusion law is just a set F together with a symmetric map, which takes two elements of F and returns you some subset of F. So I'm thinking here of F being maybe quite a small set of size 3 or 4, say. And we'll see what role it plays now. So I'm going to, just a bit of notation now, I'm going to write a lambda for the lambda eigenspace of the adjoint of some element A. So I'm going to, if I want to sort of more properly, I would say of the element A, but I'm going to drop that a bunch of the time. Okay, so suppose we've got a fusion law, then some element of my algebra is going to be an f-axis if it satisfies the following properties. So I want my element to be an idempotent, so that means it squares to itself. I also want my element to be semisimple. So that's going to mean it decomposes the algebra as a direct sum of eigenspaces. And moreover, the eigenvalues here are going to lie in the fusion law. So the fusion law you can think of as a set of eigenvalues for these axes. And then finally, the multiplication must obey the fusion law. So what do I mean by that? I mean that if you take a lambda eigenvector and a mu eigenvector and you multiply them, you must lie in the sum of the eigenspaces, which is given by lambda star mu in the fusion law. So in this way, the fusion law is giving you partial control over the multiplication in your algebra. It's at least letting you control, in a certain sense, the multiplication of eigenvalues for an axis. Okay, and we're going to say that an axis is primitive if the one eigenspace is has just dimension 1. And since we're assuming that our axes are idempotents, the idempotent is definitely in the one eigenspace. So this is so our axis is primitive if the one eigenspace is spanned by the axis itself. There's nothing else in there. And we're always going to assume that our axes are primitive. So you can take that as part of the definition of an axis, if you like. Okay, so that's what an axis is. It's a rather sort of special element in our algebra. And what are some examples of some fusion laws? So we often display fusion laws via a sort of multiplication table. So here are two particular fusion laws. And the way I write the table is I don't write all of the set symbols in the cells here, because that would just make it look a bit untidy. So when I say 1, 0, I mean the set containing 1, 0. So this is eta star eta equals the set containing 1, 0. And the empty gaps here, well, that's the empty set. Okay, so this fusion law here is the Jordan type fusion law. And this one here is the monster type fusion law. So it's just one larger. And you can see a sort of Jordan fusion law, sub-fusion law here. And we're going to say that an algebra is of monster type if it has the monster fusion law, M alpha beta. So, sorry, I should have said here, alpha and beta are just two numbers which are not equal to 1 and 0. And I also want them not to be equal to themselves. So I want 1, 0, alpha and beta to be distinct, because we're thinking of these as eigenvalues. And then similarly here, eta is distinct from 1 and 0. And likewise, we could say an algebra is of Jordan type eta if it has this Jordan type fusion law. Okay, and you will notice here that I have drawn some pretty colors on these fusion laws. So this is to indicate that the fusion law is graded. So if we look here, the red part or the pink part is the positive part, and this blue part is the negative part. And you can see that whenever I do positive times positive, I get positive, positive times negative is negative, and negative times negative is positive. And similarly for this monster type fusion law, this is also graded. So what role does this grading play? Well, the grading on the fusion law is going to induce a grading on the algebra. So remember, the fusion law is a set of the eigenvalues. So I can take all the eigenspaces, which are in the positive part, and call that the positive part of A, and the negative part is the sum of the negatively graded eigenspaces. And now, because the multiplication in my fusion law satisfies the multiplication in my algebra satisfies the fusion law, that means that if I define a map in this way, which fixes all the positive elements and negates all the elements which are in the minus part, that means that this map is going to be an automorphism of the algebra. And we've got one of these automorphisms for each axis. And because the decomposition into eigenspaces is different for each axis, we get a different automorphism for each axis. And it's these we use to generate the Miyamoto group. So hopefully you'll have seen here that the Miyamoto involutions are these naturally occurring maps, automorphisms, and we get this naturally occurring Miyamoto group. And just to sort of indicate to you that it really is sort of natural for the algebra, our motivating example of the Griess algebra, if you look at that Miyamoto group, the Miyamoto group of that algebra is in fact the monster. So that's the full automorphism group of the Griess algebra. Okay, so hopefully that's persuaded you that this is sort of a natural concept. So let's think about that first fusion law I told you about.
Excuse me, I have a question.
Yeah, sure.
You mentioned that previously that Miyamoto group is a subgroup of automorphism group, right?
Yeah.
And now you say that exactly Miyamoto group is okay, coincides in this, but automorphism group of the Griess algebra, the Griess algebra,
yeah,
is exactly Miyamoto group.
Yes.
Well,
yeah, exactly.
and it is generated by 2, 3. How many idempotents? Can you just repeat?
Yeah, so the monster sporadic group can be generated by 3 2A involutions, and these 2A involutions, so it's a particular class of involution in the monster, and these 2A involutions are in actually bijection with the axes, which Norton called 2A axes, so some idempotents in the Griess algebra. In general, in an axial algebra, so in that specific case, not only is there a bijection between the axes and the automorphisms, these 2A involutions, those 2A involutions generate the entire automorphism group. In a general axial algebra, you don't necessarily have a bijection between the axes and a set of automorphisms. You can have 2 different axes having the same automorphism, Miyamoto involution. But also, the Miyamoto group isn't necessarily the full automorphism group. So in this particular case of the Griess algebra, it is, but that's not true in general. And we'll see exactly that that's not true for the Highwater algebra.
Yes, thank you, Justin.
Okay, great. Thanks for that. So thinking about axial algebras of Jordan type, they have this fusion law here. And actually, so we want to go about classifying axial algebras, and a good way to think about splitting them up is by fusion law. And actually, I could have done one more slide here with just 1 and 0 as the fusion law, and it would look just this little subpart here. And that fusion law we call the associative fusion law, and you can show that all of the axial algebras with that fusion law are associative, and any associative algebras have that fusion law. So we've classified, if you like, the axial algebras with that fusion law as being associative. So the next most simple case to look at is axial algebras with this fusion law, this Jordan type fusion law. And so Hall, Rowan, and Shpectorov proved the following result, that every axial algebra with this fusion law, where eta is not a half, is something called a Matsuo algebra. And every Matsuo algebra with eta not equals a half is an axial algebra of Jordan type. So if you like, this fully describes this eta not a half case. So I don't quite want to tell you what Matsuo algebras are, but they have a fairly easy definition. They're defined in terms of 3 transposition groups, and their Miyamoto group is the 3 transposition group that they are defined from, well, at least up to center. So you can think of those as being in bijection with the 3 transposition groups, and 3 transposition groups have been classified by Fisher, at least the centerless ones by Fisher, and then later by Hall, by John Hall and somebody else who I can't quite remember. Okay, so what about the eta is a half case? Well, okay, maybe I've given the game away here by calling it the Jordan type fusion law. Many of you will know that in a Jordan algebra, you have idempotents and they have eigenvalues 1, 0, and a half. And in fact, whenever your Jordan algebra is generated by, so actually all these idempotents are axes in your fusion law, axes in the Jordan algebra. And whenever the Jordan algebra is generated by these, the Jordan algebra is an axial algebra with this fusion law, with eta as a half. So that's another example here of an axial algebra of Jordan type a half. And the conjecture is that those are the only examples. So you can define Matsuo algebras with eta as a half. You also get Jordan algebras, but the conjecture says that's it. And this is currently an open conjecture, although progress towards it has been made in the last couple of years. Okay, so you can see, hopefully, that for axial algebras of Jordan type, we have a fairly good understanding of what they are. So what about axial algebras of monster type? This is perhaps the next most simple example we could think of. And the Griess algebra is an axial algebra. And as you might have guessed from the name here, the Griess algebra is an algebra of monster type for the values alpha is a quarter and beta is 1 over 32. So maybe this hints to us that if we're trying to classify all algebras of monster type, this is going to be quite a lot more difficult than for the Jordan type case. So actually, this seems like a very hard problem. So the way that the classification worked in the Jordan type case is it started by classifying the algebras which were 2 generated, and then using those to classify the ones which were generated by more axes. So maybe we start here by trying to classify the monster type algebras, which are 2 generated, so generated by 2 axes. So that's what we're going to do. And one more little detail here, or one thing which is going to make it easier, if our algebra has an automorphism which swaps the 2 generating axes, we call such a 2 generated algebra symmetric. So these double angle brackets are my notation for generated by, rather than spanned as a vector space, so generated as an algebra. Right, so what we can do is think about the symmetric 2 generated algebras. And in fact, these are being classified mostly by Yabe, and then the characteristic 5 case was cleared up by Clara Franchi and Mario Mainardis. I say here actually in different years, this was, so it looks like Yabe's came first, sorry, second here, but these two have both just been published, and actually Yabe's bit was in 2021, and I think maybe Clara and Mario's was slightly later in 2021 or maybe 2022. I can't quite remember, but the Yabe classification came before. And so what's the result of these two? Well, the result of these says, if you're one of these symmetric 2 generated axial algebras, you are one of the following. You're either an axial algebra of Jordan type eta or of Jordan type beta, alpha or Jordan type beta. So I said earlier, if you remember, that I could see inside the monster fusion law a Jordan type subfusion law. So it could be that there is no beta type, no beta eigenspace in the algebra. So that would be of monster type, just with a trivial beta eigenspace. So it would be an axial algebra of Jordan type alpha and of monster type alpha beta. And similarly, you could get Jordan type beta and monster type alpha beta. But anyway, we're in pretty good shape for these because I've said that we've classified these already. And okay, actually the 2 generated ones of these are certainly classified. So what else could it be? It could be one of 12 explicit families or their quotients. And Yabe basically listed all of these. So we have explicit algebras for all of these, and they only have a few quotients, and those are known. Or the final case, you are a quotient of the Highwater algebra, or its characteristic 5 cover, which is this H hat. Okay, so this looks great. Looks like we're in good shape for this. So what's the problem here? Well, these axial algebras of Jordan type, the 2 generated ones have dimension less than 3, or most 3. So this is really nice. The 12 explicit families have dimension at most 8. So again, this is very nice. But the Highwater algebra and its cover are infinite dimensional. And we want to think, and if we want to classify all of the symmetric 2 generated axial algebras of monster type, we need to understand all their quotients. So actually in this case, there are only, so all these quotients are well understood. So really the question is, can we understand all of these quotients in the Highwater algebra case? So that was precisely Clara, Mario and my goal, to try and do this. And we actually get a very nice description of the quotients in this case. So having sort of set up why we want to do this, in the remainder of the talk, I'm going to tell you what the result is. So in this talk, I'm just going to talk about the Highwater algebra, but actually you can think of similar results holding for this characteristic 5 cover. But to make things simpler, I'm going to talk about the Highwater algebra only. Yeah.
Excuse me, interrupting again,
Sure.
but just to have a complete picture. So you said the monster algebra, okay, is generated by 3 idempotents, right?
Yes.
Now we have 2, and this classification is for 2, but in symmetric position.
Yes.
So to speak, it's very natural to think. So it's the first step. So monster is generated, okay, monster algebra is generated by 2 symmetric and something else, right?
Yes.
In this case, it's natural pre-sequel, right? Or preceder, okay. I mean, this situation should be a natural starting point. And so my question is it natural also to ask what is 2 generated algebra, but with 2 not necessarily symmetric axes, or it?
Yes, that is a natural question. So there is work currently underway. So myself and Clara and Mario and Sergei Spektorov and probably some other people as well are interested in removing this word symmetric. So there are known some non-symmetric algebras. We don't think, or we don't necessarily know the full list. We probably don't know the full list at the moment, but we would like to be able to classify the non-symmetric ones as well. So then we would be able to remove this word symmetric. And then, yeah, you're exactly right. Then there's the question of, we now know the small building blocks of the 2 generated algebras. Can we glue these together in nice ways to be able to classify all of the monster type algebras? I think that's going to be pretty hard because there's many more situations. There was a particularly nice case for the Jordan type algebras. So I think that's going to be much more hard in this case, but yes, that's the general direction of travel.
Yeah.
Okay. So having said that, I won't tell you about the sort of general case. I want to give a quick 1 slide, like aside, on what the paper actually does, or what I'm hiding in this talk. So in this talk, I'm only providing a sort of simplified version of the results, in that I'm only talking about the Highwater algebra and not the cover. So the cover is a bit more involved, and actually, in order to deal with it, what we do in the paper is we define a cover of the Highwater algebra in all characteristics, not just characteristic 5. So having just told you that there's this theorem which classifies all of the 2 generated algebras with the monster type fusion law, well, that means that in characteristic 5, it can't be an axial algebra of monster type. So for characteristic not 5, it actually has a slightly larger fusion law. So there's 1 extra element here. So instead of being a monster type fusion law with 1, 0, 2.5, it instead adds this extra 5/2. And so you might think, and you would be right, that in characteristic 5, this eigenvalue becomes 0. And so it actually ends up equaling the cover of the Highwater algebra, because it has just the eigenvalues 1, 0, 2.5 in characteristic 5. And it turns out this fusion law is of monster type then. Okay, so we define this cover in all characteristics. There's a naturally defined ideal J in the algebra so that a quotient of it is the Highwater algebra. So what we then do in the paper is we actually classify all the ideals in this new cover for all characteristics. And because we do that, this then gives us a unified classification for the ideals both in the Highwater algebra, just by taking an extra, just by quotienting by J and my ideal I'm quotienting by, and the quotients of the characteristic 5 cover, which is just the algebra in characteristic 5, at the same time. So we get this unified classification rather than having to do a classification for the Highwater algebra and a separate, similar but a bit more complicated classification for the cover. So having said that, you can now forget all of what was on this slide and just think about the Highwater algebra for the rest of the talk. So I haven't actually told you what it is, so I should probably do that. So again, this was defined both by Clara Franchi, Mario Mainardis, and Sergei Spektorov, and by Yabe in the classification paper. Both of these results were on the archive in 2020, within a month or so of each other. So the dates here are the published dates. Okay, so what is the Highwater algebra? I've already said it's an infinite dimension algebra. It has basis given by some elements AI and some elements Sj, where the AIs run over the integers and the Sjs run over the natural numbers. And so I need to tell you what the multiplication is. So the multiplication is as follows. If you do AI times Aj, you get half of AI plus Aj plus S of the difference between the I and J. So if you like, the S elements here are measuring the distance between the A elements. Yeah. And when you multiply an A element by an S element, you get sum of the A elements and then sum of two other elements, A elements, sort of distanced apart by J, below and above, and another bit, and then something for the J's. So actually, this multiplication isn't as terrible as it might look at first glance. It actually is quite nice. And so one other thing is that S0, we set that to be 0 in the algebra. So this Sj runs over the natural numbers, so not including 0. S0 is 0, which means that here, if you do AI times AI, you get a half of 2 times AI, well, that's AI, plus 0. So that means that the AIs are idempotents. And it won't surprise you to learn if the first fact I tell you about this algebra is that each AI is not only an idempotent, but it's actually an axis for the monster type fusion law with the particular values 2.5. And we have enough of these AIs. So each one of these AIs is an axis. So there's an infinite set of axes here, but the whole Highwater algebra is just generated by a pair of them, say A0 and A1 will generate. So that's showing that the Highwater algebra really is a symmetric two-generated axial algebra of monster type. So what about the Miyamoto involutions? So I'm going to write tau of I for tau of AI, just a bit simpler notation. And this acts on the axes as a reflection in 2I. So if you like, here are my axes all lined up. And the tau involution for A0 is a reflection in 0. Yeah. So it's just performing that reflection. And so you can immediately see that the Miyamoto group, which is generated by all of these tau elements, acts naturally on the set of integers, well, the axes, which are isomorphic to the set of integers, and it acts as the infinite dihedral group here. But actually, I only ever get reflections in each axis like this. So I only get translations by 2 in the Miyamoto group. However, there is another automorphism. It's exactly the one which makes the algebra symmetric, i.e. it swaps A0 and A1. So this performs like a reflection in a half. So I'm going to call this tau a half. And so this another reflection. And so you can see that 0 and tau a half is also an infinite dihedral group. And it turns out, you have to show this, but it turns out that the full automorphism group is exactly this group. And so we see that the Miyamoto group has index 2 in this full automorphism group. So here is a case where the Miyamoto group isn't the full automorphism group, it has index 2. Okay, so those are some facts about the Highwater algebra. So what about ideals in axial algebra? So I need to tell you a little bit about those, because that's what we're trying to classify. And the results come from this paper of mine, Sergei's, and Sanhan Khazar's. So one of the results in it is that every ideal in an axial algebra is invariant under the Miyamoto group. And turns out this will be important for us. And also in this paper, we split ideals into 2 different classes. So, and we deal with them in 2 different ways. So the first of these is ideals which contain an axis, and the second is ideals which don't contain any axes. So that seems like a fairly natural split. So one property which is going to help us to identify ideals is if the algebra has a nice bilinear form. So what do I mean by nice? I mean that it has a bilinear form, which we're going to call a Frobenius form, which is non-zero and which sort of associates with the algebra product. So what I mean by that is that if I do A comma B times C, that's the same as A times B comma C in the algebra. And it turns out that the Highwater algebra has a Frobenius form, and it's actually a very nice form. The value between any 2 axes is 1, and the value between an axis and one of these S elements, or between any 2 S elements, is 0. So it has a very nice form. And in fact, if you know about such things, it turns out that this makes the Highwater algebra into a Baryk algebra. But that's not going to be important for us. So how does this help with with ideals in axial algebras? So we said we split them into 2 different types. So I want first to think about those which contain axes. And in that paper, we showed that if we have an axial algebra which has one of these Frobenius forms, then if we've got an axis which is in our ideal, and we have another axis which is non-zero in the form, so A is in my ideal, B is another axis, and A comma B is non-zero, then B must also be in my ideal. And so what we can do is we can define a graph on the axes. So we're going to call this the non-commuting graph. And we have an edge between 2 elements if their value in the form is non-zero. And so using this, we're looking for sort of connected components in the non-commuting graph. And well, I already said for the Highwater algebra, the value between any 2 axes is always 1. And so for the Highwater algebra, the non-commuting graph is the complete graph. And so it doesn't have, so any non-proper ideal, sorry, let me say that again. No proper ideal contains any axis, because as soon as you contain one axis, you contain all the axes, and those generate the full algebra. Okay, so we never have to think about ideals which contain axes for the Highwater algebra. So what about the other type of ideals? Ideals which don't contain any axes. So in that paper, in that other paper, we define something called the radical, which is the unique largest ideal which doesn't contain any axes. So we define this thing and we show that it's unique. And it turns out it's easy to identify it using the Frobenius form. So we prove a theorem there which says the following. It says if you've got a Frobenius form, then the perp, so the perp with respect to the Frobenius form equals the radical of the algebra if and only if the value of all the axes is non-zero in the form. And of course, the radical of the Frobenius form, this A perp, is very easy to work out because it's just a bilinear form. So that's just some linear algebra. And if we look at what the radical of the Highwater algebra is, we look at the radical of the Frobenius form, and it's easy to see that it's the difference of any two axes, and also all the S elements are in there. However, it turns out that has codimension 1. It's easy to see it's got codimension 1 in the Highwater algebra. So actually here, that hasn't helped us too much. We've got this unique largest ideal, which contains all the other ideals, but it's codimension 1 in an infinite dimensional algebra. So at first glance, it looks like this hasn't helped us very much. However, it does give us this key property. So if we've got some element, I can write that as some sum of the A elements and some sum of the Sj elements, linear combination of each. Suppose that element X is in my ideal. Because that is, if that's a proper ideal, it must be contained in the radical. And therefore, the sum of these AIs, the coefficients AI must be 0. Sorry, alpha i's must be 0. So that's our first key property. So remember that I said that ideals are invariant under the Miyamoto group. So what about for the Highwater algebra? Well, the Highwater algebra, the Miyamoto group has index 2 in the full automorphism group. And a theorem that we show in the paper is that actually every ideal is not only invariant under the Miyamoto group, but it's invariant under the full automorphism group. So this might seem like a pretty small step, but actually it turns out to be very important in our classification, and it allows us to significantly simplify all the rest of our arguments. And I will hint at least some of the simplifications in a couple of slides' time. I also say this isn't actually that easy to prove. This is 5 pages worth or something to prove this, so it's not just trivial to show. Okay, this also has an immediate corollary. So we now know that not only are all the quotients 2-generated axial algebras, but they're all symmetric 2-generated axial algebras because of the extra automorphism here. Okay. So another key result is the following. So we show that every ideal of the Highwater algebra is a principal ideal. And we use a sort of rather involved Euclidean-like algorithm to do this. And from this theorem, this is, as I say, another key result for us. We get the following corollary. This implies that every ideal of the Highwater algebra has finite codimension. So again, this is going to really simplify our arguments. In other words, if every ideal has finite codimension, that means all the quotients are finite dimensional. So we've already learnt something about the quotients. In particular, the axes in the quotients must, because they all lie in a finite dimensional space, they must span a finite dimensional subspace of that. So again, an easy observation. And we're going to say that, therefore, the axial codimension of the ideal is D, if the axes span a D-dimensional subspace. So they don't have to span the full quotient. In general, they won't. And this is actually what Yabe called the axial dimension of an algebra. So we're just using that and calling the axial codimension of the ideal, which gives that quotient. D is the same here. Yeah. Okay. So if we've got this axial codimension now, we can think of classifying ideals with a given axial codimension. And what we do is the following. So if we've got an axial codimension D ideal I, we show that there exists alpha 0 up to alpha D, so that this sum here is in the ideal for some alpha 0 up to alpha D, with alpha 0 and alpha D being non-zero. So we've got some tuple of alpha i's which make this sum live in the ideal. And actually, this is now very easy to see, because what does it mean to have axial codimension D? So this should say axial codimension. That means that A0 up to AD, so those, I'm thinking about the images of those in the quotient, it means that they must be linearly dependent, because these axes, they're D plus one of them, they span a D-dimensional space. So we must actually have some alpha i's where this is true. So now we've just got to show that alpha 0 up to alpha D is, alpha 0 and alpha D are non-zero. The rest could be 0. So for a contradiction, suppose that alpha 0 is 0. Now, since the ideal is invariant under the full automorphism group, I can take translations here. I can move AI to any other AI, so I can translate, and I can get the sum to also be in I. And so I can take differences and show that actually the image of all the axes span a subspace of dimension at most D minus 1. Oh, but that's a contradiction, because the axes must span a dimension D subspace. So actually this, showing that the ideal is invariant under the full automorphism group, has allowed us to have a simple linear algebra argument to show this result. And again, we can refine this argument slightly to give us our second key property, which is that actually these alpha i's, we can't choose them all independently. So there exists some epsilon, which is plus or minus 1, so that alpha I equals epsilon alpha D minus I for all of the i's. Yeah. And we prove it in a very similar way. So instead, this time we pick a reflection switching A0 and AD. And so this reflection has flipped, if you like, all of these alpha i's here. I'm thinking about this rather geometrically. And then we just take linear combinations and we get this result. So that's actually rather easy to show. Okay, so now let me put all these together. Remember, we had that was our second key property there. Our first key property was that the sum of all of the alpha i's had to be 0. I've also got that alpha 0 and alpha d have to be non-zero. And this is my second key result, on which I just showed. So what I'm going to do is I'm going to just define a tuple of elements. I'm going to say that they're of ideal type if they satisfy these three properties. And then the result that we show is the following. We show that if you've got an ideal type tuple, then there's a bijection between the set of all ideal type tuples up to scalars and the minimal ideals of axial codimension D. And this bijection is just given by sending this tuple of elements to the sum of alpha I times AI and the ideal generated by this element. So actually, this is a really nice result. And this gives us all of the minimal ideals in the Highwater algebra. So not only do we have this theoretical result here, which is very nice and much nicer than you might have expected, but we also get an explicit basis for the ideals. So suppose we've got one of these minimal ideals, and it's generated by an ideal type tuple, alpha 0 up to alpha d. Then actually the ideal is spanned by, and you can cut out these to get a basis fairly straightforwardly, but it's spanned by the sum of all these alpha i's times I plus k. So again, these are translates of these for all k. So I can take all possible translates, or I get this, which I'm going to say now is a folded version. I'll draw you a picture in just a minute, of the S elements. So what's the picture? How should you think of these? So here in the blue is one of my X elements. So this is X minus 1. So I'm thinking here of a ideal where my D here is 6. I've got alpha 0 up to alpha D, up to alpha 6 is my ideal tuple. And I've got all translates xk. So this is X minus 1. So I've drawn you on a number line here. So I've translated this. So it starts alpha 0 times, alpha 0 times a I minus 1, alpha 1 times lots of a 0, and so on. So I've got all possible translates. And then this S version, remember, I've only got S elements for 1, 2, 3, and upwards. I don't have them for 0 or any of the negative numbers. So what this element corresponds to is this red element here, where if you like, I folded this here, and I've got all possible foldings. And when I fold, I lose this alpha element here. So I don't have any of this because that's times S0, which is 0 in my algebra. But I do have alpha 1 plus alpha 3 times S1, alpha 0 plus alpha 4 times S2, alpha 5 times alpha minus 1. Well, alpha minus 1 is 0. So that's just alpha 5 times S3, alpha 6 times S4. And that's it for this example. Yeah. So there's this very nice geometric picture. So what all of the elements which span my algebra, my ideal are, and depending on what the foldings are, you can get rid of a few of these and make it a basis very easily. Okay, so the final thing I want to note is that this particular tuple is an ideal type tuple. So 1 with all zeros and then minus 1 at the end is an ideal type tuple. And so in particular, the ideal generated by A0 minus AD is a minimal ideal. of axial codimension D. And what does this mean? This actually means that we have a quotient of the Highwater algebra which has exactly D axes given by the images of all of these axes. So I only get D distinct images. And this has about D plus a half D dimension. And so why is this interesting? Well, previously, we only knew about axial algebras which have axial algebras of monster type, the two generated ones. We only knew examples of these which had 2, 3, 4, 5, 6, or infinitely many axes. And so this result shows that we actually have examples of these for any, with n axes, for any n being a natural number or infinity. I guess we did know 1 here, but 1 is just the trivial algebra with a single idempotent. Okay, so that is all I wanted to say. You can find the paper on the archive. Thank you.
Thank you.
Thank you, Justin. Are there any questions?
Oh, that's actually the wrong order. There's the names. Sorry, Mario. I've only just spotted that you should be before me. I obviously can't do alphabetical order.
Yeah, it depends whether that C is being considered as a letter or no. Or independently.
Well, even then he's got that.
I even know if we skip, yeah, the second one will be I.
Yeah.
Yeah.
Justin, I guess these alphas, they're up to a factor, right? You can always assume that alpha 0 is 1, right?
Yeah, exactly. So I said in this, I'm taking the ideal type tuples up to scalars. So yeah, exactly as you say, I can always mod out. Yeah, you could think of these as a projective, if you like. Yeah, so you can always make alpha 0, 1, or whichever other one you want to divide by, whatever's convenient.
I have a question also, so maybe general, so I understand that this is a talk about ideals, but in general, so those Highwater algebras, do you have some intuition they have to be connected to some identity, to some model? For instance, can one try to search for a model which is isotopic? It's a good model which is isotopic to this Highwater algebra and something else. So just to believe that this is not accident example, so it should be some good description. Do you have already something, or do you have some intuition, or?
No. So I think I'm right in
so
saying.
I just, excuse me, I'm interrupting, just to understand my question. For instance, there are some like Virasoro algebras, maybe like not exactly, or not exactly what one can do, but there is some good model. For instance, one look at holomorphic functions, and here we are, okay, here's some object, but maybe associative, of course, but I mean by isotopy, and this infinite dimension could be sort of maybe some, not necessarily holomorphic model, but something like series with just regular multiplication, by then nothing such.
No. So I think I'm right in saying that in general, if you've got an axial algebra, or at least the ones we know about, and you try and look for an identity which all of the elements in the algebra satisfy, so like how you might define other non-associative algebras by some kind of identity or series of identities, you can't find any identity which isn't just one which ends up saying, here are some axes, here is the fusion law, all of the eigenvalues must satisfy, or it must have this given fusion law, it must be, the axes must be semisimple, and so on. You can't find any identity which says any more than that. And I also don't know why like the Highwater algebra comes out as this exception. So that's actually a really interesting question. You know, why does it occur like this? So one observation I could make is that the Highwater algebra is for the value beta is a half, and it has infinitely many axes. The other axial algebras, the two generated ones of monster type, which we know of, which have infinitely many axes, also occur for beta is a half. So somehow this is something special about the negative part, if you like, the beta being a half might correspond to giving you infinitely many axes and having some exceptional behavior. That's the only sort of vague, well, thing that you can spot. I don't have a good explanation for it. But it's a really interesting question. I'd like to know one.
One more question.
Justin, I think there is a result that in the Highwater algebra itself, there are no further x's apart from the AI, yeah? What
Yes.
about quotients? I mean, quotients is probably not known, yeah? Is it?
In some cases, so it's not known in general. I do know of an example I know of an example of a quotient of the Highwater algebra. So that's an axis. The axis is of type 2.5, but it's not only graded with respect to the half, it's also graded with respect to the 2. So it turns out it's an axis of type 1/2, 2, as well as 2.5. So actually in the paper, we show a result which classifies all of the quotients of the Highwater algebra, which is like doubly graded like this. And all of the examples, not quite all the examples, but some of the examples are isomorphic to some of Yabe's examples. And so this turns out that there's actually, in some of those cases, there are additional axes which can be got by applying like the automorphism with respect to the 2 grading, will get you another axis that isn't one of the ones you see as an image of the Highwater algebra ones. So in summary, in some quotients, there exists additional idempotents, even having the same fusion law as the quotient, as the normal axes do.
And what kind of automorphism groups you get with this additional automorphisms? Are they very different from the dihedral groups?
I think in that case, you get the full infinite dihedral group and some other stuff. I don't think we worked out what the full fusion law is. I'm quickly zipping through the paper to try and remember what the algebra is. It's an algebra with 6 axes, and I think 5 of those. So one of them is, if you like, the image of one of the ones from the Highwater algebra. The other 6 are new ones, but of course you can translate those other 5 by the infinite dihedral group. So it's got quite a larger group. We haven't figured it out actually, but I can talk to you afterwards about what the algebra is there. We know the algebra, we just haven't figured out what the additional one is, additional automorphism group is, like the rest of it.
I have a question. Why do you call them Highwater algebra?
So that is down to Clara, Mario, and Sergey. So they found the algebra when Sergey was visiting Clara and Mario in Venice. And that particular time, there were floods in Venice. And so they called the algebra, the Highwater algebra. It's not quite called like that in their first paper, although I think there's a comment to it somewhere there, but it's too good a name not to call it that. So everywhere else, the Highwater algebra.
Thank you.
Well, we are almost out of time. Is there any other question? Well, if not, let's thank Justin again, and I think we can stop.
Thank you.
Thanks
Thank
very
you,
much.
thank you for your presence. Thanks for the nice talk.
Very nice talk. Thank you.
Thank you.
Thank you. Thank you, Justin.
Thanks.